Okay. Yes. Thank you. So good afternoon to everyone. So I'm really glad to be here, even if I would like to meet you in real, but it's already a wonderful opportunity for me to present the work we do in Paris. And I warmly want to thank Boris for the organization of this seminar. So as he said, I am Hélène Pillet. I am a professor in Arts et Métiers Institute of Technology, and I belong to a human biomechanics lab. And during the next hour, I would like to show you how we use biomechanics in order to improve the design of mechatronic prostheses. So I know that some of these work are very close from the ones that are done here in Georgia Tech. So I would be very happy if we would have the opportunity to have scientific exchange and, if possible, to collaborate together. So on this first slide, you can see a woman who is wearing a prosthesis, but I don't know if you can see the particularity of this prosthesis. Something that's normally is not feasible when you are amputated at the level of the thigh, so above the knee. So to help you, you can have a look to the position of the lower limb joints, and you can see that the ankle, the knee, and the hip are all flexed, which is normally not doable with a transfemoral prosthesis. So you can see that it is very useful when you want to go downstairs because you can have your foot flat on the step. So this prosthesis, its name is Sensis, and it is the result of a research collaboration between my laboratory and a French company, which is called Proteor. And this prosthesis has been put on the US market in 2024. And I think it perfectly illustrates the title of my presentation, and I will use it as a guiding theme of this presentation. But first, let me present you briefly where I come from. So I am in the Arts et Métiers, which is one of the oldest engineering school in France. This school has 8 campuses all over France, and I belong to the Paris campus. So in this campus, my laboratory gathers about 10 full-time faculty members and 20 PhD students. You can see here a map of our facilities, which includes a technological platform of more than 1,000 meters square. And we have a lot of experimental devices. So here it is the EOS system, which is a stereoradiographic system. The particularity of the system is to be a very low dose irradiation system, which allow the 3D reconstruction of the human being skeleton, as you can see here for the spine. We have also some test beds to study in vitro specimen in both static and dynamic conditions. We are also able to perform some mechanical simulation of the behavior of the human body through finite element modeling, for example. We have an experimental surgery room where we are able to instrument the cadaveric specimen before testing. We have a GET lab equipped with an optoelectronic system with 15 cameras and 4 force plates, and also electromyographic system and wearable sensors. We have an ultrasound elastography, and finally, we have acquired very recently an instrumented treadmill and a gas exchange measurement system. And here are also the rooms we use for the training of the students. So in this laboratory, our focus is to model the neuromusculoskeletal system of the human being in a personalized way. And this is then applied to two fields, two different fields. First, clinical and surgical innovation, and particularly orthopedic systems. And in the field of sport, mobility, and handicap. And in this field, we are particularly interested in the interaction between the human being and the environment, and including the assistive devices or the sport equipment. So as you know, studying the musculoskeletal system of non-amputee people is not trivial at all because of the great number of bones and muscles that compose this musculoskeletal system. So the muscles can be either monoarticular or biarticular. They can contract in different modes, eccentric or concentric, and all of this being controlled by the central nervous system. So if we want to take into account all this complexity, it can be very, very difficult. And beyond this, in this presentation, we will focus on people who have lost a part of this musculoskeletal system, which has to be replaced by a prosthesis. So when the amputation is performed at the level of the thigh, it is called a transfemoral amputation, and we have to replace both the knee and the ankle with a prosthetic knee and a prosthetic foot. This prosthesis is then linked to the residual limb by the socket. So what is very challenging is that the prosthesis has to cover not only flat walking, but also a multitude of activities depending on the lifestyles of the users, as it is illustrated here. And so the notion of personalization of the prosthetic control is very crucial in the prosthetic design. So a lot of designs have been proposed since the first artificial leg of Ambroise Paré in the 16th century. For example, there have been a lot of different mechanical architecture. Hydraulic units were also added, and highly elastic materials used in order to mimic the action of the muscles in the prosthesis. But today, the wide majority of these prostheses are passive, and so they cannot deliver energy to the user. One advantage of these passive prostheses is that they are very light, and this is very important when you think that they have to be actuated by the muscle of the hip only. But the limitations of this device appears quickly in the everyday life environment, and particularly slopes and stairs can be very difficult and requires a special attention from the user. And this is mainly due to the unadapted stiffness of the ankle, which prevent the correct motion of the foot. It decreases the support basis and can lead to specific strategies to overcome the impossibility to perform some motion, such as going down the stair. Here on the movie, you can see that the user have to put the foot on the edge of the step to be able to go downstairs. So it is obviously very detrimental for the security of the stance phase during this motion. Also, the absence of mobility of the ankle during the swing phase is a source of tripping because it decreases the distance between the two and the ground. So finally, the fall and the risk of falling are real limits for the use of prosthetic limb. And we can see that the prevalence of fall is twice higher for transfemoral amputee compared to older non-amputee subjects. Also, the limits in the functionality of the prosthetic joint will lead to compensations, which can, at the long term, expose the residual joints to secondary pathologies such as osteoarthritis. And last but not least, it is well known that the cost of the locomotion is higher for people with amputation. So since the 70s, robotic solutions have been developed in the research laboratories to try to solve these different issues. And if these prostheses have succeeded in reproducing the kinematics and the kinetics of the physiological joint, they have had relatively modest impact on the clinical outcomes, which can be a bit surprising. And particularly, they have not succeeded in decreasing significantly the metabolic cost. On the contrary, they have some drawbacks such as weight, noise, or autonomy, and these often lead the users to abandon these prostheses at the profit of mechatronic prostheses. So to come back to the questions of this presentation, I would like to emphasize the use of biomechanics to improve the personalized control of the prosthesis. So this is a topic I have been worked on with my colleague, Xavier Bonnet, who is associate professor for now about 15 years. So my presentation will be divided in 4 parts. Corresponding to the issues we have identified during the introduction. So first, improving the prosthetic control. Second, decreasing the metabolic cost. And third, preventing walking instability. But first, I would like to introduce the prosthesis I have shown you on the first slide, the Synthesis prosthesis, because I think it is a good example of the interaction we have had with the company in order to go from the laboratory prototype to a final product, a commercial final product. So this story starts in 2011. At that time, we obtained a grant from our National Agency of Research to study the locomotion of people with amputation in challenging situations of everyday life. So this project was the framework of the PhD of Coralie Villa. And we have worked with the company, Proteo, and 2 rehabilitation centers. And we have collected the data of more than 100 subjects working in 5 situations of everyday life reproduced in our lab. So you can see these situations on the slide. So from this data, and still in collaboration with the company, we were able to propose a microprocessor-controlled prototype without motorization in 2014. So it is the device you can see in the center of the slide. The originality of this device is to be biarticular. So it embeds both the knee and the ankle in the same mechanical architecture, and both joints are actuated by the same hydraulic unit. So the control of the two joints is shared, and this is to mimic the action of the biarticular muscle of the calf when they actuate the native knee and the native ankle. So after a lot of evolution and 10 years more research, we were able to develop the final product called Synthesis that was put on the market in 2023. So this prosthesis is basically a microprocessor control knee ankle prosthesis. And the microprocessor uses a minimal set of sensors to measure the knee angle, the tibia angular velocity, and the ankle joint moment. And at the high level of control, they are used by a finite state machine to identify gate phases and situations of locomotion. So during the stance phase, 4 situations of locomotions are differentiated: level ground, slope ascent, stair descent, and slope descent. Also, during the swing phase, we are able to assess stumbling and walking velocity. So the advantage of this kind of finite state machine is that it is transparent, deterministic, and interpretable by both the designer and the user. However, obviously, the complexity of this machine will grow fast if we multiply the number of activities to be identified. Yes. Yes.
How many actuators this prosthetic device has? 1 or 2?
There is no actuator. It is, yes,
So
it's passive. So the hydraulic units modify the resistance of both joints depending on the activity. So for example, when you go down the slope, you have to increase the resistance of the knee in order to be able to put some loads on your prosthesis with the knee flexed. So it is what it is controlled in the prosthesis, and the behavior of the knee and the ankle is
so the resistance is the controller. So
yes, exactly.
Like passive.
Yes, yes. Then at the intermediate level, we will, for each phase of the gait cycle on each situation, determine the behaviors that the prosthesis must have. And to realize this adaptation, we will modify a model of impedance which link the joint moment to the joint angle. So finally, the resistance of the joint. So concretely, to do that, we have to adjust the stiffness, the damping, and the position of equilibrium of each joint. And to choose the ideal value, we use the data collected on non-amputee subjects in the different walking conditions. So we try to apply what we observe on non-amputee subject to the prosthesis. Finally, the last level is called also the low level and correspond to the mechanical and hydraulic architecture we will be used to realize concretely the adaptation. And this is a very difficult layer to implement because we have to meet a lot of standards in order to be able to transition from this kind of prototype, laboratory prototype, to a commercial product that meets the safety requirements to be used in the real life. So this movie shows you the preliminary test that was performed 10 years ago, and you can observe the fluidity of the motion, the control of the users on the prosthesis, the synergetic behavior allowed to realize some motion with involve the flexion of the three joints of the lower limb, such as going down a stair, making some squats, or lacing one's shoe, for example. Another advantage of this prosthesis compared to other prostheses on the market is that you can adjust the height of the heel. So you can walk either barefoot or with high heels, which is very appreciated by the users. So 10 years after, and a crossover clinical study have been necessary to put the device on the market. But the story doesn't end here, because there are progress to do in the control. Today, if the algorithms are configurable, they are not optimized for each individual, and they are not specific of certain conditions. So, for example, the adaptation of the knee is the same when going downstairs or downslope. So if we want to progress, we know that we have to work on the prosthetic control, and so it will be the topic of the second part of this presentation. So first, we would like to try to use machine learning techniques in order to improve the high-level detection. So this was done in the PhD of Boris Doriac, and we have collected some data of people working in predefined scenarios where the situations were labeled. We have extracted from the sensors embedded in the prosthesis a lot of mechanical descriptors and use them in different machine learning algorithms. So these algorithms go from fully interpretable, like decision tree, to completely black box, like SVM. And they performed very well on the situations where they have been trained for, but they are still facing the question of the risk management, because if you perform 10,000 steps per day, even an accuracy of 99.9% will result in 10 errors per day. And this is an illustration of what can happen when the algorithm make a mistake. The behavior of the prosthesis will be not adapted to the situation, though here the knee is blocked when the user wants to go upstairs. And in some situations, it can be very dangerous and increase the risk of falling. So another direction to improve the prosthetic control is to do it directly at the intermediate level. So this means that we want the prosthesis to react correctly, independently of the explicit identification of the situation it is encountering. So this is well illustrated by this jumping robot. So you can see that this small robot is able to continue its course without knowing it will encounter an obstacle or knowing the height of this obstacle. So this is referred as reflex adaptation. And in that case, to adjust the impedance parameters of the model, we will use gait characteristic extracted directly from the sensors, the same sensors embedded in the prosthesis. And in our work, we have chosen to use the kinematics of the center of mass to adjust the parameter of the model of impedance. But to do that, we have to be able to estimate the position of the center of mass in real time. And it is also a big challenge. So it was the topic of the PhD of Clément Durafour. And in his thesis, he first used some IMUs, so inertial measurement unit, put on the lower limbs and the pelvis. And finally, at the end, he limits them to 2 IMUs, put only on the prosthesis, so on the shank and on the side. And you can see in the middle of this slide the results of the estimation of the center of mass with the estimation from the IMUs versus the reference from the optoelectronic system. So what we can see is that we have a long-term drift of this position, but this is not a major issue, because we are more interested in the velocity. If I can show. No. No. We are rather interested in the velocity of the center of mass, because we think it is predictive of the situation of locomotion and that it evolves inside the cycle, and we can use it to adapt continuously the parameters of the model of impedance. So this is supported by the graph you can see on the left side of this slide, which represent the vertical velocity of the center of mass in different conditions of walking, represented by the different colors. So as you see, the vertical velocity evolve inside the cycle. And if we link the parameters of the model of impedance to this variable, we should be able to adapt it all over the cycle.
What are the units on the...
Yes, it is a normalized vertical velocity. It's why it's because between strange units. Yeah. So we have tested initially this kind of adaptation with people who are not experts. There are some non-amputee people who are trained to use orthoses to be able to walk with the prosthesis. And this allows us to adjust the parameters of the control to decrease the asymmetry of the step lengths and the loads on the contralateral limb. And we have obtained quite interesting preliminary results. So now we are testing this adaptation with real users. And the first results we have obtained are particularly promising for making control more specific, transparent, and intuitive. So we have to continue the work, but we think that it is a good way. So let's move now to the second topic, which is the decrease of the metabolic cost. So since the 60s, the energy consumption of people with amputation have been quantified. And 2 recent reviews of the literature show that it is increased for people with amputation, which can partly explain also the decrease of their activity and autonomy. And what is striking on the graph on the left side is that it increases way faster when you are amputated at the level of the thigh, so above the knee. So you can see that the oxygen consumption is twice the one of below knee amputee or on non-amputee people for above knee amputee. So it is the green curve on this slide. So if we want to design more efficient prostheses, it would be very interesting to relate this metabolic cost to the mechanical work performed by the body on the prosthesis. So we have done that in the PhD of Lucas Sedran. We have first proposed to model the gait by a succession of inverted pendulum movement. So in this kind of modeling, we can consider that very little energy is provided during the single stance phase. But on the contrary, during the double stance phase, it is necessary to reorient the velocity of the center of mass. And so some energy will be used by the contralateral limb to perform this reorientation, and which will depend on the work performed by the trailing limb during the propulsion. And when you are amputated, the work performed by the prosthesis will decrease compared to a physiologic limb, which will be compensated by the contralateral limb, which has to provide more energy. However, this increase in the energy produced by the contralateral limb does not explain the experimental increase observed of the metabolic cost. So to better understand, we have designed a caricatural experiment, again with northosis, when we have asked a non-amputee subject to wear two prostheses, one equipped with an energy storing and release foot. So this kind of foot on the top, which are carbon made and that are able to store and release energy at the end of the stance, thanks to the deformation of the material. And the second foot at the bottom, you can see that it is totally rigid. It is 3D printed, but with a rollover profile, which allow to keep the same motion of the center of pressure, but without any restitution of energy due to the deformation. So we have measured the gas exchange with these two prostheses on the simulator. And as the model, the inverted pendulum model performed bad, we have also designed a musculoskeletal model of the lower limbs, because we hypothesize that the discrepancy between mechanical work and metabolic cost could come from the loss of efficiency of some muscles. So the musculoskeletal model we have designed in the postdoc of Bonnet-Lebrun is very simple, with only 11 muscles and classical heel model and criterion of the minimization of the square of the activation of the muscle to determine the forces in the different muscles during the motion. Then we use an empirical metabolic model of Minetti to be able to estimate the metabolic cost of each muscle during the motion. So it was we had done on 8 non-amputee people working on the instrumented 12 minutes to validate this model. We have used a comparison with the electromyography to check the activation of the muscles. And we have measured the metabolic energy through the gas exchange measurement. So the graph here represents the experimental metabolic cost versus the metabolic cost estimated from the model. And we can see that this model is able to capture the increase of the metabolic cost with the speed, which was already shown by Coelho, Winch and collaborator in 2018, because here we have 3 working velocities. So Then we were able to use this model for the 3 conditions with and without a simulator. So here are the results of the metabolic cost for each muscle. For the lower limb without simulator, here for the first bar. Then with the simulator on the deformable foot for both limbs, the prosthetic and the contralateral one. And then for the simulator with the rigid foot, also for the prosthetic and the contralateral limb. What we observe is that the metabolic cost is decreased for the limb which use the prosthesis, but this is normal because some of the muscles of the lower limb are not used, such as the muscles of the shank. And on the contrary, the metabolic cost of the muscles of the contralateral limb is increased. So to have the overall metabolic cost, we can sum all the contribution of the muscles and compare this metabolic cost to the experimental one coming from the measurement of the gas exchange. Unfortunately, this musculoskeletal model failed in capturing the big increase of the metabolic cost we observe with the gas exchange. Indeed, you can see that the increase is 2 times the one without simulator when you have the simulator. On the contrary, the model is able to predict the absence of difference between the 2 prosthetic foot, the deformable one and the rigid one, which was a bit surprising for us, that there were no difference in the metabolic cost with the 2 foot, but the model also predicts the same thing. So there are a lot of perspectives to improve this musculoskeletal model, which is for the moment, as I said, relatively simple. Particularly, we want to take into account the trunk contraction, which must be non-negligible for people using prosthesis or a simulator. Also, we want to address the question of the contraction by using, for example, electromyography sensors. This is challenging because of the presence of the socket, but we will try to do it. Another way of improvement is to better personalize the geometry of the model, thanks, for example, to the EOS system, so the stereoradiographic system I present you at the beginning. But we want also to work at the personalization of the muscular properties, which can be very different for people with amputation compared to non-amputee subjects. So we try to develop some protocols that can be used in the clinical environment to capture these muscular properties. So the increase of the energy cost could also be a consequence of muscular strategy to manage the inherent instability of walking. So the last part of this presentation will focus on this, on the quantification in the first step of this instability. So to study this specific point, we have developed a collaborative work with 2 robotics laboratory, one in France, in the south of France, in Toulouse, and the other one in Japan. And it is also the framework of the PhD of Ariane Lallès. And in her PhD, we try to study mechanical descriptor of the whole body dynamic stability and to test their ability to detect the increase of the instability during walking. So the idea behind is to be able to measure this mechanical descriptor from wearable sensors to be able to monitor the instability of the gait and also to use it to improve the control of the prosthesis. So we have particularly focused on a descriptor, an indicator, a criterion that uses the minimal moment axis of the ground reaction forces and moments, and its position relatively to the center of mass. So we have proposed to study this indicator in two experimental modalities. The first one involved human subjects, so 15 asymptomatic volunteers who were asked to work on an instrumented treadmill, and which were submitted to two kinds of perturbations representing trip and slips. So here is the illustration of the perturbation for the slip. So I don't know if you have seen it, but, and the second one, is for the trip. So here the band will stop. So in the first case we accelerate the band, and in the second one we stop the band. So the perturbation is set at the beginning of the cycle for each perturbation. So the second modality used a humanoid robot. So in the laboratory in Japan. So in this case, we use some obstacles in order to perturbate the gait of the robot, and in some cases, we this perturbation lead the robot to fall, to an actual fall. And so from the sensors of the robot, we were also able to compute the same kind of parameters that we can compute for the humans. So here are an example of the results we obtain for the parameters during the walking and during the perturbation. And these results are still under analysis, but we can see that we have a promising results in detecting the increase of the instability due to the perturbation. We have the same kind of result for the robots. We can see here the increase of the value of the parameter, and the big increase correspond to the fall of the robot. In the same time, we are developing a shoe which will be instrumented with some magnetic sensors in the insole. And the big advantage of this insole will be to be able to measure not only the vertical force, but also the forces in the anteroposterior and mediolateral axis, which is not possible for the moment with pressure insoles. So to conclude this talk, if I come back to the question I have asked at the beginning, I think we see now how biomechanics can be used to make assistive device more personalized, more intuitive, more efficient, energically efficient, and safer. But the road is still long, and as it is said in this citation of Eberhard, we can say that this task is probably never ending. So we have a lot of perspectives to the work we are already conducting. One of these is to progressively include the human in the loop of control. This not only to optimally adapt the control, but also to provide feedback of the prosthesis behavior to the user. And we have recently applied for a European call to be able to work on this topic. So in parallel, we have also other research action with my colleague Pierre-Yves Rohan, who is associate professor in the lab. And so we supervise the PhD of Hélène Pillet, who have instrumented some 3D printed socket in order to be able to measure not only the pressure, but also the shear force at the interface between the residual limb and the socket. This is to improve the design of the socket and limit the skin, the problems that can occur at the level of the skin and in the deep soft tissues also. But in the future, this kind of instrumentation could be used also for the control of the prosthesis. So I would like to acknowledge all my colleagues and my students who have worked on all these topics. We have also other topics. I have no time today to present about the wheelchair locomotion, but all these work are focused on the interaction between the human body and the assistive device. So I thank you very much for your attention, and if you have some questions, I will be very happy to answer now.
Hopefully, Melody can.
Yes. Oops, I can. Yes.
How do you compute the energy expenditure in the model?
With the muscular model, we use the empirical model of Minetti, which relate the forces, the activation forces and velocity of the contraction to the metabolic cost per muscle.
Yes, I remember that.
Any questions in the chat? I'm not seeing any right now, but feel free to unmute yourself if you're on Zoom as well. Thank you so much, Dr. Pillet. That was a really, really interesting talk.
Thank you.
It's not exactly related to the presentation, but it is a curiosity question about the robot.
Yeah.
When we saw the robots, I noticed that the posture of the leg of the robot had that very strong degree of deflection.
Yes.
And when it fell exactly the way I would expect a person to fall if their center of mass was perturbed and their knee was extended far in the anterior direction relative to the rest of their weight. I would expect them to fall backward. I'm curious if that is the normal posture for the robot.
Yes, it is the normal posture of this kind of robot, and it is due to the way they are controlled, because they use the what we call the zero moment point. So it is finally the sort of center of pressure that they must keep in the polygon, the rotation polygons, and by using this posture, it's far easier. So if you have a look to the humanoid robots in the world, you will see that most of them work with this flexed posture.
It's easy to control.
Yes, exactly.
Only on flat surfaces.
Yes, yes, yes.
So it takes more energy to walk like this, right? Because you need to.
Yes.
You need.
Yes.
Flex. Humans. That's.
Yes, but these robots are not very efficient from the energetic point of view.
So you don't know if there are any robots that walk like humans. They use pendulum mechanism.
There are some, but they are limited. They cannot perform a wide variety of motion. So it's a sort of trade-off. You have to choose what you want to do. And so for these sophisticated humanoid robots, I think it's normal to work like that.
Oh, it looks like we have a question on Zoom, Hansel.
Thank you for the talk. I was curious about whether you have any thoughts on using metabolic cost as a measure of the performance. So it seems like biomechanics community has been focused on reducing the metabolic cost on amputee walking and such. But seems like recently people are realizing that maybe there are other more important things to optimize for. Like, so do you think metabolic cost really matter? What are other things that you think are important?
I think metabolic costs matter because if you have a big metabolic cost, you will not be able to perform. It will decrease your level of activity, and it's what is observed for these people. It is not the only thing to address, for sure. The functionalities of the prosthesis is also very important, but finally, metabolic cost at the end is a good way to evaluate the performance of the device, because normally, if the function is better, we would expect a decrease of this metabolic cost at the end. So it's a very global, it's also a very global evaluation. I think it is not the only one we have to use, but it is informative of the level of functionality and clinical outcome also.
Any other questions in the chat?
No, I think there is no other question.
You mentioned machine learning use. Is it possible to tune parameters of the prosthetic device to teach it, to minimize energy expenditure over multiple repetitions of the task?
Yes. Is it, I think, the idea of the human in the loop control? So the idea is to be able to adapt the parameters of the prosthesis according to the cost we can measure for each individual. But this is already done for exoskeleton, for example. But for the moment, it fails when using a prosthesis for the studies that were published in the literature. But we think that it will be possible in the future, and particularly it will be possible if we are able to measure the metabolic cost continuously. It is why these musculoskeletal modeling are very promising and useful, because the measure with gas exchange necessitates 5 or 6 minutes walking to have a stable measure of the metabolic cost. So it is not very adapted to modify the settings of the control.
Did you try to verify your computed energy cost with the measurement?
Yes, yes.
So
Yes, for non-amputee people, it's okay. But for people with amputation, it's not okay.
so you need to...
So we need to refine the model for this kind of people. And yes, it can be due to the simplification, too simple model, because we have only the lower limb for the moment, so we want to put also the trunk. It can be due to the fact we don't take into account the contraction. And also it can be due to the mechanical properties of the muscles that should must be different for people with amputation compared to non-amputee.
One more thing.
I have a question in the room.
Sure, go ahead first.
Yes. Sorry, can you repeat? Yes. Yes. The energy in the heel for the deformable foot. That's your question?
This
Yeah.
spring
Yes. Yes.
in the heel.
Yes. Yes.
The question is whether you can use a similar mechanism for the front.
Yes. There is already.
Second.
Yes. Yes. For the carbon foot is already deformable all along the foot. And so is able to store energy at the different phase of the stance when you go forward. And so the release of energy is really at the end of the stance. But the question of when the energy is released is very important also. So we have to work also on the design of the foot in order to be able to retrieve all the energy, and particularly one issue is that at the end of the stance, you have to flex the knee. So the release of energy can be lost due to the initiation of the flexion for the swing. So this is a very difficult to tune and require to well think to the design of the foot in relation with the knee. So it's why biarticular prosthesis is very interesting also, and not separated components. Yes, so there is another question. Yes.
Yeah, so I think one other aspect of prosthesis control is that amputees have altered sensory feedback.
Yes.
So what is your thoughts on how that altered sensory feedback affects the control of locomotion? And do you have any plans to, I don't know, incorporate like some feedback sensors, like haptic feedback, or some providing some alternative measures?
Yes. So for the moment, I think that the sensory feedback is poorly taken into account in the prosthetic that are on the commercial market, but it would clearly be an improvement to be able to provide this sensory feedback to the user. And so it's one of the topic we want to work on in the future. And for this, we can use the socket and try to implement some way of giving some sensory information to the user. But for the moment, I think there is no commercial versions that include this kind of sensory feedback. But for sure, it is an area of research currently.
Do you have a guess on what is the most important information that they need to receive?
But I think the proper what should be the proprioception at the level of the foot is very important. So this can be acquired by insoles, I suppose, that could be put in the shoe. But also the position of the joints could be very informative for the subject. Also, as we have some sensor of motion, I suppose it could be possible to give this information. The question is perhaps how to give this information. And for the moment, I have no clear idea for that. Especially if we don't want to perform a surgery. We want to do that at the external part of the residual limb.
Would it be possible to use the vibration of the
Yes.
tissue muscle to
Yes,
activate?
I suppose it could be possible to use vibration. And I think some teams are working on this kind of sensory feedback, but I don't know enough about this work, but I think it's a way, yes.
I have a question kind of along the same lines. Or I guess too, because I might have missed something in your presentation. You mentioned the musculoskeletal model and reflex control. How are the reflexes implemented in your musculoskeletal model right now? I think I missed that
Yes.
part.
So the reflex control I mentioned was not for the musculoskeletal model. It was for what we call the reflex adaptation of the prosthesis, because it is a way to have the prosthesis to adapt itself without the high level of control. It is what is called reflex adaptation, but finally it is not really a reflex. It is only that you tune the parameters of the model of impedance of each joint depending on parameter characteristic of the gait. And in our work, we have chosen to use the kinematics of the center of mass, but it can be another parameters that is used to modify the behavior of the joint in real time, depending on these parameters. So it is different from the identification of the situation that can be done at the high level of control by classification of the situations.
That makes sense. I was also wondering, like along the same lines of the discussion you were having a minute ago, it's, even though it's a passive prosthesis, might it be possible to have something analogous to interjoint spinal reflexes where the ankle impedance is affected by the knee angle, for example?
Yes, this is what is done in the prosthesis I presented you. For example, the dorsiflexion of the ankle is directly linked to the flexion of the knee. So I have not presented this, but we have a mechanical link between the knee and the ankle. So when you flex your knee, there is an automatic dorsiflexion of the ankle, which is useful, particularly during the swing phase. So it's like this. So flex and up. There is the dorsiflexion of the ankle. And it is useful both during the swing phase to avoid to improve the toe clearance. And it is useful also when you go, for example, down a slope or a stair, because as the knee flexes, the ankle will flex in the same time. So it is limited to a certain angle, but it provides this synergy between both joints. And it is the way we are able to have the three flexions of the three joints of the lower limb. And this with other transfemoral prostheses where the knee and the ankle are independent is not possible.
Can this mechanism work in the opposite direction when you expand the knee? This wind helps to extend. the
Yes, so no, because we would need to provide energy, and with our device, we have no energy to, if we have to push, for example, on the floor, we have to be able to provide energy at this stage. So it's
but-
why we have not this link, so it's reverse link. So the plantar flexion at the beginning of the stance is automatic
Nice.
under the force, the ground action force. But we cannot have this, it would be very interesting to have the extension of the ankle at the end of the stance phase, but it's not possible without providing energy at this stage.
How about landing? Landing, you want to
Yes.
use the energy of the body. You
Yes.
have dorsiflexion,
Yeah,
and that would flex the knees well, right?
yes,
Gently. So that might be similar mechanism.
Yeah.
You don't need damage.
yes. Yes. It seems it's okay. There's no more question in the Zoom.
Okay, do we have Melody here? I guess we can disconnect.
Yeah, before you disconnect, can everyone on Zoom, you don't have to unmute, but thank you so much, Dr. Pillet, that this was a really, really cool experience, and I'm so glad everyone got to experience it despite inclement
Thank
weather.
you. Thank you.
So I'm not there in person right now, but I know someone was asking if normally we do like a social hour afterwards, and I don't know what your plans are, but if anyone who is in the talk physically right now wants to continue the conversation, I definitely encourage you to do so, depending on what Dr. Pillet's schedule looks like and her interest. So yeah, thanks so much for attending, and our next neuromechanics talk will be at the end of next month. It will be Halloween themed. You will see more information about that soon. But yeah, thank you so much, Dr. Pulitsky, for helping organize this.
Thank you, Melody.
Thank you. Thank you very much.
All right, so we can disconnect.